If you were to take like the fastest supercomputer on the planet today, power it up, and ask it to find the absolute perfect, mathematically optimal solution to a large scale NP hard network problem, well, you'd be waiting a very long time.
Yeah, literally longer than the current lifespan of the universe.
Right. The heat death of the cosmos would actually happen before that machine could check every single combination. But you and I and the engineers designing the microchips that basically run our world, we don't have a few trillion years to spare.
No, definitely not. We need answers in milliseconds.
Exactly. So, welcome to another deep dive. Today, we're taking a look at a massive computational bottleneck, the minimum weighted vertex cover, or MWVC. And I want you to picture the scene here. My guest is sitting in front of this shifting digital cityscape that's like morphing into this massive web of interconnected computer networks.
It's quite the visual.
It fits the theme perfectly. Because our mission today is to track this problem from the elegant, pure mathematical theories of the 1980s straight down into the raw, bare metal execution of modern silicon hardware.
And we're using two specific slide decks to do this. Scaling vertex cover algorithms.pdf and vertex cover.pdf. It's just a fascinating trajectory. We're essentially looking at the friction between theoretical math limits and physical engineering.
Okay, let's unpack this. For anyone who might not look at graph theory every day, what exactly are we dealing with here?
Right. So imagine a graph for just a bunch of dots, which we call vertices, connected by lines, which are the edges.
Simple enough.
Yeah. But here's the catch. Each dot has a specific weight or cost attached to it. The goal of the minimum weighted vertex cover is to pick a subset of those dots so that every single line is touching at least one of the dots you picked.
But you want to do this while spending the absolute minimum amount of total weight.
Precisely. You want the cheapest possible combination that still covers every single connection. But because this problem is NP hard in general, finding that perfect, true minimum at scale is just mathematically impossible.
So you have to guess.
Well, not guess, but approximation algorithms aren't just a nice shortcut. They are completely mandatory. We have to design algorithms that guarantee a good enough answer that's mathematically bound to the optimal solution, even though we will never actually know what that optimal solution is.
Okay, to kind of ground this abstract math, let's look at a really specific localized example from the sources, the triangle graph.
Oh yeah, that's a perfect starting point.
So we have three vertices forming a closed loop, a triangle. Vertex A has a weight of 1, vertex B is heavy, it has a weight of 3, and vertex C has a weight of 2.
Right, so to cover all three connecting lines for the lowest cost, the optimal cover is obvious. You just pick A and C.
Because that gives a total cost of 3, and every single edge is touching either A or C. It's clean, it's totally verifiable.
Exactly. But you can't brute force that logic when the graph has a billion vertices. Which brings us to the first major strategy from the decks. The primal dual LP formulation.
Which gives us a deterministic 2 approximation, right?
Yes. But instead of getting bogged down in linear programming matrices, the source offers this really elegant gap metaphor to explain it. Imagine every vertex in the graph is a physical container.
Okay, I'm picturing it.
The total capacity of that container, the gap, is initialized to equal its weight. So go back to your triangle. Vertex A is a container that holds exactly 1 unit of volume.
And B holds 3 units, C holds 2. So they all start completely empty.
Correct. Now, the algorithm iterates through all the uncovered edges. For every violated edge, you begin pouring water, which is our dual value, into the containers of both endpoints simultaneously.
At the exact same rate.
Exactly the same rate. And this water reduces the remaining empty gap for both vertices. The second that any container's gap hits 0, that vertex is fully paid for, and it instantly snaps into our cover set.
So the pouring stops for that edge.
Right. And the core mathematical rule that makes this work is that the sum of the gap reductions, the total water you poured in, is always less than or equal to the total weight of the chosen cover.
So if I'm understanding this, it's almost like two people sitting at a restaurant splitting a bill.
Okay, I like where this is going.
They're connected by the table, right?
Okay.
One person has $10 in their wallet, so their gap is 10. The other person has 50. They start tossing money onto the table at the exact same rate, dollar for dollar.
Right.
And the instant the person with $10 is completely emptied out, their gap hits 0, they are forced to basically pay for that connection. They get pulled into the cover set, and the financial bleeding just stops for both of them.
That is a brilliant analogy. It captures the simultaneous reduction perfectly.
But wait, if we are just blindly iterating through these edges and pouring water into these pairs, couldn't we accidentally overpay?
How do you mean?
Well, what if we max out a container, add that vertex to our cover, but then later down the line, we max out other adjacent containers that technically cover all the same edges anyway. Wouldn't we end up with a bunch of expensive, redundant vertices?
Ah, you have hit on the exact trap of the primal dual approach, the redundancy trap.
I knew there had to be a catch.
There is. Phase 1 is greedy. It frequently overshoots. Therefore, a secondary cleanup phase is mathematically mandatory. We call this the reverse delete phase.
So you have to work backwards to fix your mistakes.
Exactly. You process the vertices in the exact reverse order that they were added. You take the very last vertex added, temporarily remove it, and just check the adjacent edges.
And if those edges are still covered by other dots in the set,
Then the vertex you just removed was completely redundant. You permanently delete it. If you don't do this, you lose your strict minimality guarantee.
it's like a panicked grocery run. Phase 1, you're just throwing everything into the cart so you don't starve.
Right, just grabbing everything.
And then phase 2 is standing at the checkout, pulling items out in reverse order, asking, do I really need a fourth box of cereal based on what else is in here? And if the answer is no, you toss it.
That's a very practical way to look at it. But even with reverse delete cleaning things up, deterministic algorithms harbor a really massive vulnerability.
Because they follow strict rules.
Exactly. They can be completely manipulated by the specific order of the input data. We call it the deterministic vulnerability.
Oh, this is the 100 versus 1 trap from the sources.
Yes, lay it out.
So imagine just two vertices connected by one edge. Vertex U has a massive weight of 100, and vertex V has a tiny weight of 1. Any human looks at that and instantly picks V, the cheap one.
Of course. But a fast, deterministic, greedy algorithm doesn't have intuition. If the edge processing order is stacked against it, it's going to blindly follow its rules and pick the cost 100 vertex.
Which is a disaster.
A total disaster. Across different permutations, your expected weight could average out to around 50, which is just abysmal. The rigidity of the rules becomes a huge liability.
So if the strict rules fail, you have to inject chaos. Or, well, probability.
Exactly.
Yeah.
This brings us to a major pivot from the 1980s, Pitt's algorithm. Published in 1985. Pitt realized deterministic gaps were too brittle, so he introduced a randomized coin flip.
But it's not a fair 50-50 coin, right?
No, it's a mathematically biased coin. When Pitt's algorithm looks at an uncovered edge, it uses a randomized selection that heavily favors the lighter endpoint, based on the inverse proportion of their weights.
Okay, here's where it gets really interesting. Let's apply Pitt's math to that 100 versus 1 trap.
Let's do it.
To find the probability of the algorithm making the stupid choice, picking the heavy 100 weight vertex, the formula takes the weight of the other vertex, which is 1, and divides it by the total weight of both, which is 101.
Right.
So 1 divided by 101. That means there's less than a 1% chance the algorithm makes the wrong choice.
And conversely, the probability of picking the optimal light vertex is 100 divided by 101, so a 99% chance of success.
It's like a rigged roulette wheel. Almost the entire wheel is painted with the winning cheap outcome.
What's fascinating here is the absolute mathematical certainty you get from that randomness.
Yeah.
By using this bias flip, the expected cost for covering any edge mathematically resolves to exactly 2 times the minimum weight of its endpoints, or less. Yeah. And when you scale that up, you secure the 2x guarantee. Even with random coin flips, the total expected cost of your entire cover will never exceed exactly 2 times the optimal perfect answer.
So you give up absolute step-by-step control.
But you gain total robustness against tricky input data. The order doesn't matter anymore.
That is some brilliant 1985 math. But, fast forward to 2026, we aren't using chalkboards anymore. We are running this on massively parallel silicon architectures.
Yes, we are.
And it turns out Pitt's 40-year-old algorithm is actually the ultimate setup for modern GPU execution because it requires 0 state sharing.
That's the real magic of it. In hardware scaling, performance is all about state sharing, or ideally the lack of it. When you look at the GPU accelerated numba CUD approach from the sources, the whole goal is concurrency.
Because GPUs just want to go fast.
Right, and Pitt's algorithm evaluates each edge independently. There's no global water level to track, no shared containers. A thread processing one edge doesn't have to talk to a thread processing another.
So the strategy is just a massive Monte Carlo simulation. Fire off thousands of independent trials all at once to find a good cover just by sheer statistical volume.
Exactly, but we hit a massive physical bottleneck here. GPUs are amazing at parallel volume, but they absolutely hate branching logic.
Right, because of warp divergence.
Yes, GPUs group threads into bundles, usually 32 threads to a warp, and they all have to execute the exact same instruction at the same time. If one thread hits an ISIL statement and takes a different path,
The whole warp fractures.
exactly, the hardware literally forces the diverging threads to sit there idle while the others finish. It destroys your efficiency.
And bringing it back to the math, the reverse delete phase is entirely conditional branching. If this is covered, delete this, else keep it.
You nailed it. Because of warp divergence, the GPU approach completely abandons the reverse delete phase. It just runs the raw phase 1 Monte Carlo trials. And honestly, just getting that to run requires insane engineering.
Yeah, because you can't just use standard random number generators on a GPU, can you?
No, standard RNG libraries use global states or memory locks. If 10,000 GPU threads ask for a random number at once, the system crashes. So they have to build a device-side linear congruential generator.
An LCG.
Right, an LCG that relies purely on local thread math. And on top of that, they can't even store the data as regular Booleans. They have to use bit mask packing.
Wait, packing the data into 32-bit words?
Yes, unsigned integers. So a single GPU instruction can process 32 vertices at the exact same time using bitwise logic.
That is just nuts, the lengths we go to just to brute force probability at scale.
It really is. But remember, the GPU isn't the only hardware path. The sources also map out the CPU multi-threaded approach using C++20 standard async.
Right, and CPUs are a totally different beast. A CPU doesn't have thousands of cores, it might only have 16 or 32 threads, but they are sophisticated, they handle nested branching logic without a problem.
Which sets up the ultimate trade-off in the master decision matrix. The GPU runs millions of trials, but produces dirty covers without the cleanup. The CPU runs way fewer trials, but every single thread executes the full, strict reverse delete sweep.
Okay, I have an analogy for this. Tell me if this works.
Let's hear it.
The GPU approach is like releasing a million hyperactive bees into a maze. They just blindly bump into the walls, moving as fast as possible, and through sheer volume, some of them find the exit.
No reverse delete, just pure speed. I like it.
Right, but the CPU approach is like a small team of highly trained detectives. They methodically sweep the room, and most importantly, they double-check their work with that reverse delete sweep to prune out false leads.
That maps perfectly to the reality of warp divergence versus CPU branch prediction. And, recognizing this hardware divide actually drove the evolution of the software stack itself.
Oh, moving from Python to C++R, right.
Yeah, they started with a Python prototype, netless stacks. Great for quick iterations, but Python's global interpreter lock ruins hardware-level parallelism. So they built netless stack CPP.
The C++ production architecture.
Exactly. It's a strongly typed, template-based powerhouse. It's graph agnostic, weight map agnostic, and totally RNG agnostic. You can just plug and play different mathematical models to test the hardware limits.
So, what does this all mean for you, the listener? We've talked about math from the 80s, warp divergence, and C++ templates. Why do we care so much about finding minimum dots on a graph?
Because of electronic design automation, EDA.
Building microchips.
Exactly. The chips in your phone or server farm have billions of transistors, and they aren't just connected by simple lines. They use nets that connect multiple modules at once. It's a hypergraph generalization of the exact problem we just spent this whole time discussing.
So, optimizing this math physically builds the technology you're using to listen to this deep dive right now.
It dictates how hot your phone gets and how fast it runs.
That is wild. I want to leave you all with a final provocative thought pulled from the Future Horizons slide. We've talked about the GPU's massive scale, the B's, and the CPU's high-quality cleanup the detectives as two totally separate paths.
But what if you didn't have to choose?
Exactly. Imagine a hybrid GPU plus CPU architecture, a system where the GPU acts as the massive brainstorming generator, instantly firing off thousands of rough drafts.
And then it seamlessly hands the absolute best ones over to the CPU.
Right, and the CPU uses its sophisticated branching logic to run the reverse delete validation. It's combining rapid, unstructured brainstorming with meticulous, structured refinement. And honestly, think about how that hybrid approach might apply to your own problem solving in life. Start with the B's, finish with the detectives.
I love that.
Thanks for joining us on this deep dive. We'll catch you next time.